Howdy everyone, Professor Parks, PhD here, and welcome to the channel. This video is a talk that Dr. Swati Mohan gave at the beginning of May, and it details just how phenomenal an engineering feat it was for Perseverance to be launched and landed successfully on Mars. Dr. Swati Mohan joined NASA Jet Propulsion Laboratory first in 2004 after completing her Cornell University in Mechanical and Aerospace Engineering. After working as a systems engineer on Cassini during Saturn orbit insertion and Huygens probe release, she returned to graduate in 2005 to MIT. And yes, this is my cat Luna, if you were wondering whose tail this is. Where was I? Dr. Mohan received her MS and PhD in aeronautics and astronautics from MIT Space Systems Laboratory. During her return to JPL in 2010, Dr. Mohan has worked on multiple missions such as GRAIL and OCO3. For the past 8 years, she has been the lead guidance, navigation, and control systems engineer for for Mars 2020 Perseverance Rover, focusing on cruise and EDL. In 2020, she transitioned to Mars 2020 guidance, navigation and controls operation, lead and mission commentator for the landing of the Perseverance rover on February 18th. She essentially was known as the voice of the rover, or the voice of Perseverance, who gave play-by-play during that critical 17 minutes it was deployed from its orbiting spacecraft and to when it hit the touchdown on the Martian soil. She's currently the guidance, navigation, and controls lead for the Psyche mission, which is scheduled to launch in October 2023. Dr. Mohan has also co-founded and manages the Small Satellite Dynamics Testbed. I will apologize. The first part of the talk, I didn't hit the record button fast enough. It will start pretty much in progress. The only part that you would miss, just a small introduction to history, Mars exploration. So without further ado, if you really enjoy learning about the technological aspects of NASA's missions, or just the engineering wonder of it all, I believe that you will truly enjoy the following. So thank you, and peace out, clear skies.
Opportunity actually basically hit a hole in one. They were able to identify that there was water very early on in their mission. They were designed to last for 90 days. And they actually ended up lasting for years and years. So over the course of their lifetime, they identified water in different forms in terms of things that were in lakes and rivers, water that was very acidic, as well as water that could have been more neutral. So it was a huge success. With that, we were able to really determine that there had been water on Mars. The next mission in the rover lineage is Mars Sample Laboratory, which is the Curiosity rover in 2010. This is Curiosity. It's about the size of a car, like a PT Cruiser or a mini Jeep. And Curiosity was going to Gale Crater in order to find this water. A few years after this, I think it was around 2015, Curiosity was able to determine not just the evidence of past water on Mars, which is what Spirit and Opportunity were able to do, but evidence of current liquid water on Mars. And that's huge, right? Now, with the evidence of current liquid water, as well as Curiosity's discoveries of the building blocks of life, the chemical composition, the chemical components of what life needs, like the carbons and the nitrogens, we had all of the pieces that we thought were essential for life. We had the liquid running water of neutral pH. We had the building blocks of carbon and nitrogen. Now the next step was, can we actually find the signs of past life? And this is Perseverance's main goal. Now, in order to get there for Perseverance, we had to do things a bit differently. Spirit and Opportunity were small-ish rovers, right? The size of a kid's toy car. So our method of landing them on Mars was basically to cover them in bubble wrap and let them bounce around until they were slow enough. So we came in as a ballistic mission, jettisoned the parachute, and then when we were close enough, we literally inflated these big bags, sort of like bubble wrap, all around the rover. We lowered it on a bridle and then cut the thread of this bubble wrap encased rover bounced on the ground over and over again until it eventually slowed down and it was to a halt. And then it popped the balloons from the inside, lowered the panels, and then drove off. When we tried to do this with Curiosity, it didn't work. The rover was way too big. Every time the force of the bubble wrap encased rover landing on the ground when we were doing our testing would rip these bubbles to shreds and poke holes, and then that would kind of negate the safety effect of the bubble wrap. So Curiosity designed a new way of landing on Mars, which was the sky crane maneuver, where we used retro rockets to hover above the ground and lower the rover wheels down onto the surface in order to land there safely. Now, Curiosity could do that also because Curiosity went to basically a parking lot next to the thing that it wanted to explore. So Gale Crater had a big ejecta in the middle called Mount Sharp. And then there was a big flat area in the center of the crater. And Curiosity basically found a big enough, flat enough, rock-free enough place in the center to land. And that's essentially like finding the smooth parking lot outside of the, the actual area of interest or the hike or trail that you're needing to go to. That method didn't quite work for Perseverance because the point of trying to find evidence of past life, you actually need to go to where we think had the best chance of preserving that past life. So for Perseverance, the scientists and engineers decided on Jezero Crater. This is a color warp map of Jezero Crater. The white circle here is Perseverance's landing area. And you can see that this area there are a lot of things going on in this area. So if you look from the top, you can see this, this channel flowing down. This is where we think there was an actual like river channel flowing in to Jezero Crater. This is the rim of Jezero Crater, and you can see this beautiful ejecta here of all these sediments coming in and flowing into the base of Jezero Crater. We think Jezero Crater may have been an ancient lake bed. So what you're looking here is kind of the differences in that tier of the lake. So you have the initial higher ground river channel flowing into it, and then the shallower part of the river. And then you know how you get far enough in and it kind of drops off and you get a deeper lake bed? That would be this bottom portion over here of the deepest, flattest portion of the bottom of the lake bed. Now, these have a bunch of relief in it, and that's exactly what the scientists like, because you can land in one place and you can actually drive with Perseverance to many of these different regions, right? If you land in this region, you get this sample. You can go to this wall, which is almost 800. Which is this one I think is around 300 to 500, and then this one is more than 800 meters apart. I had to go back and look at my figures, but there's several hundred meters difference between the base here and the top here. And then this is also, there are enough channels that Perseverance could theoretically drive up here or maybe up into this river channel itself. So the scientists were like, this is the best place to go. They'd originally considered it for Curiosity, but it was deemed too hazardous because not only do you have a cliff here in the middle of the landing area, all of this region here is littered with rocks, big rocks of all different sizes that this river maybe came and put at the bottom of this ancient lake bed. So how do we actually land here with Perseverance in a place that we never thought we could go to before with Curiosity? Perseverance and Curiosity are very similar. They borrow heavily, Perseverance borrows heavily from Curiosity. So she's about the same size, a little bit bigger than Curiosity, a little bit heavier, but more or less the same. So in order to figure out how to land Perseverance here, we had to develop new technology so that she could land safely and wouldn't accidentally, land on the edge of this cliff and tumble down, or land on a rock here and twist her foot and be able to land safely. So I'll get into a little bit of the new technology later in the mission, but just keep in mind that we're going to a much more hazardous site than Curiosity. And the purpose of going to Jezero Crater was really to find the best evidence of past life. Perseverance's mission is to find the signs of past life and to prepare for eventual human travel to Mars, and most importantly, to bring back samples to collect the samples that can one day be brought back to Earth. In order to actually find the signs of past life and say definitively that there was life on Mars, that's a huge statement to make, right? Because that is in and of itself an answer to the question of, are we alone in the universe? And for us to be able to say that, you really need very strong, indisputable evidence. When we build these rovers, we can only send them with so many instruments, right? They have a limited set of instruments that they can actually do measurements on. So it's only if we get the samples back and we can unleash the full arsenal of the scientific technology that we have here on Earth that we would really be able to definitively say that we've found evidence of past life on Mars. That's why getting the samples back is so important. And you can't get them back until you're able to go there and find what those samples are. So Perseverance has 4 main phases. Launch, which is July of 2020. Perseverance is a type 1 trajectory to Mars, and this means that it has the shortest trajectory that you can possibly do to get from Earth to Mars. They time it just right with the planets and do basically a Hohmann transfer. So the minimum time, it only took about 6.5 months for Perseverance to get from Earth to Mars. So about less than 7 months to get to Mars from Earth, and then 7 minutes of terror to get from the top of Martian atmosphere to the ground safely. And that's called entry, descent, and landing. And then that's really just to get there and start doing the science. So the surface mission is aimed to be at least 1.5 Mars years, which was about 3 Earth years. So Perseverance landed in February 2021. So we're already past February of 2023. So we're 2 years into the prime mission, which is about 3 years, but she's still going really strong and doing all sorts of great science. So just to give you some context of the Mars 2020 mission as a whole, it comes in a lot of different pieces. Perseverance is the main piece, kind of at the heart of the rover. And you can see the wheels of Perseverance here, all tucked up into the belly, kind of all folded in. And then here you can see that broken up. So around Perseverance, we have to add all of this hardware. And all of this hardware that you see around Perseverance is solely to get Perseverance from Earth to Mars safely. So starting from the top here, this cylindrical part is what we call the cruise stage. That has the sensors and actuators, the thrusters, the little jets that help the mission navigate in interstellar space, in the vacuum between Earth and Mars. So it attaches up here. That's what these are. These gold things are the propellant tanks that actually hold the gas to get from Earth to Mars. Once we get close to Mars, about 10 minutes before we're slated to hit the top of the atmosphere, we jettison this. So this cylindrical part comes off and it goes and crashes elsewhere on Mars. And then we're left with this capsule, which is comprised of the back shell here and the heat shield, which is this big gold thing at the bottom. So the heat shield, as this capsule, it's almost like an airplane because we do guided entry. So we're maneuvering this capsule through the atmosphere of Mars at the beginning of the entry phase. This heat shield at the bottom is what dissipates all that energy from coming in at ballistic speeds, interplanetary speeds into the atmosphere of Mars. So the heat shield is what protects the rover from all that heat. The back shell here, which is this cone, white cone at the top, you can see these little cutouts. Those are the thrusters that help us maneuver during entry in the Martian atmosphere. This also holds our parachute. So we jettison the parachute from the top of this cone here, and that slows us down significantly. Once we're on the parachute, we jettison the heat shield. So the next thing that gets rid of is this gold heat shield that gets jettisoned. It also goes and falls somewhere else on Mars. And now we're coming in on a parachute with the rover tucked up underneath this. Once we slow down and have figured out where we are, we then cut the back shell. So we're coming in now with just the rover and its jetpack. This is called the descent stage. It's basically a set of huge rockets and enough smarts in order to maneuver Perseverance right above where it wants to land safely. And then it lowers Perseverance onto a bridle, which is part of this descent stage. Once Perseverance is wheels down on the ground, the descent stage or the jetpack cuts the bridle, and then it goes and flies off and crashes somewhere on Mars. So all these pieces eventually, in that span of 17 minutes or so from the start of when the crew stage jettisons, they all eventually like disperse to each other. So the only thing that's left on the ground is Perseverance itself. That whole capsule is the Mars 2020 project. We deliver that to Kennedy Space Center, and this is the integration into the Atlas V launch vehicle fairing. This is just the top of it, so you can kind of see the scale here. This is the whole Mars 2020 mission. It's getting encapsulated in this launch vehicle. There are some cabinets down here, so you can kind of get the sense of like how big a person would be, which would be like about, you know, halfway up this cabinet compared to this huge launch vehicle. Once Perseverance goes into this launch vehicle, they button up this fairing, and then they put the fairing on top of the actual engine or jets of the launch vehicle, and then they launch it. The fairing itself is this very top portion here, and the rest of it is, you know, the launch vehicle, the rocket itself, and all the rocket propellant and fuels and stuff. So this is a picture of the actual launch of Perseverance at the end of July in 2020. Smack dab in the midst of a global pandemic. We actually did manage to get off the ground within our primary launch window, which is great because, as I mentioned, Perseverance was assuming that we were going to have the shortest journey time between Earth and Mars. And to do this, you have a very narrow window that you have to hit. So there's about 3 to 4 weeks every 22 months where Earth and Mars are perfectly aligned, that if you launch during those 3 weeks, you have the shortest trip time around the solar system to get from Earth to Mars. So Earth and Mars were at their closest at the time of launch. And by the time we arrived at Mars, we'd basically done like a half circle around the solar system. And that is the most direct path for interplanetary speaks of getting from one place to the other. We had up to 6 opportunities to correct our trajectory to make sure that we were on course. But Perseverance actually had a really good injection. So we used 3 of them, and these are kind of planned maneuvers. And then with the third one, we were coming in smack dab on course, right on course. So we actually didn't even need to do these last 3 maneuvers. We were really well within our corridor at the end of our third trajectory correction maneuver. It's about 300 million miles that Perseverance travels during its roughly 6.5 months to get from Earth to Mars. So just keep that in mind, 300 million miles. And we're trying to hit a very particular region on Mars of Jezero Crater, about 8 kilometers, about 8 by 6 kilometers on Mars. And then of that 8 by 6 kilometers, which was roughly the size of that white circle, we have to find a safe spot and land to it. We had aimed for landing to it within 60 meters. We actually did much better than that, and I'll show a little bit more about that. So this goes into just the things that I said about how entry, descent, and landing works when I was describing the hardware. So about 10 minutes before entry interface, we jettison the cruise stage that's up here. So that cylinder part comes off. We have some masses on the vehicle that kept it stable and spinning like a top during cruise to keep it gyroscopically stable. We actually get rid of those and we create an offset in our center of mass. And this is because we're actually going to fly the entry capsule like a plane. So we create this offset so we have a lift vector, and throughout entry we actually do hypersonic aero maneuvering. So we're actually doing these bank turns with Perseverance as an entry capsule. So we're flying it like a plane, and this is in order to get closer to where we want to be on the ground. So just like a plane, if they're coming in too steep before they hit the runway, they do these S curves to kind of they're still descending, but they're too close to the runway. So these do the S curves to control their distance to the runway. That's exactly what we were doing with Perseverance. So once we get past peak heating and peak deceleration, which is about 10 Gs that Perseverance pulled here, we deploy the parachute, supersonic parachute over 2 meters in diameter. We upgraded from Curiosity here. Curiosity used just a velocity trigger to deploy its parachute, where it basically sends, okay, if I'm going, this fast, I'm going to deploy my chute. Perseverance did a little better. It basically deployed the chute depending on how far it was from its target, and that allowed us to get a 40% improvement on how accurately we were landing on Mars. So that one line change of code in the logic of when to deploy the parachute got us a big boost in terms of landing accuracy for Perseverance. Once we're going slow enough on the parachute, we deploy the heat shield. We have a lot of sensors that we use to do ground relative sensing to figure out where we are with respect to the ground. The heat shield is like a lens cap. It's preventing us from seeing the ground. So we deploy the heat shield. We don't need it anymore because the peak heating finished over here. And once that heat shield is gone, we use both a radar and an imager to look at the ground. The radar gives us distance from the ground, how far is our range, and then the imager helps us localize where Perseverance is. So we take images as we're descending, and this was the new technology that we added called terrain relative navigation, where we actually take images and then compare them to a map that we preloaded on board. And that comparison of taking the image and looking at the map and seeing where they fit allows us to localize and say, okay, we are here on Mars right now. And by knowing where we are, we have another preloaded map that has basically colored the whole landing site, in different shades of between red and green of what's safe, what we think is safe to land on, and what we don't think is safe to land on. So based on where Perseverance figures out where it is, it automatically decides which landing spot to target based on where it is and how far it thinks it can go. So once it figures that out, it picks its safe target, and then we've gone slow enough on the parachute that it's not going to slow us down anymore. So it's not useful anymore. So we jettison the parachute and then come down on our jetpack. As we do the maneuver to get out from underneath the parachute, we use it to go fly to our desired safe spot and then lower the rover on the bridles. Once the rover hits the ground, then we cut the bridles and then fly away. And all of this on this map takes 17 minutes. It's pretty slow at the top, and then everything from here all the way to the ground takes 7 minutes. So now I'm going to do a little glimpse of how it was on landing day.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. parachute has deployed, and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The backshell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
I still love that video every time I see it. And it's not, the imagery itself of landing was fun, but the best part to me is that these images, these are the actual images that Perseverance took. And we were the first ones to actually be able to see landing in this way. Previous missions, you know, we get the data back, we get the ones and zeros, but we don't actually have that visual. For the first time, we had put enough cameras on the whole rover in all sorts of directions that we can actually capture this footage live to see what the parachute looked like, to see what the descent stage looks like actually on Mars, not just intuit what it looks like based on the ones and zeros that come back. So that's kind of why I love watching that video, to see how it all came together and how it looked that day from Mars. So just a little bit on the technical stuff, if any of you guys are curious. This is what I mentioned. It was a one-line change of code to decide when to deploy the parachute. The blue here is what Curiosity's landing ellipse looked like. And then the yellow is the effect that we got with changing that one line in software of how to deploy the parachute. So we actually were able to improve the accuracy about 40% from this long oval to this almost circle just by that one line changing code, which is amazing for us. It, you know, a lot of bang for very little bucks. And then terrain relative navigation. So this was the big technology that we added for Perseverance in order to land at Jezero Crater. And what terrain relative navigation does, it basically uses a special computer that has fast enough image processing with a camera that is looking down during descent to take descent imagery, stitch them together using an IMU, compare that imagery to a map, localize features on the map, and use that to come up with an estimate of where we are with respect to this map. We then take a similar map where we've identified all the hazardous areas. So on this one, red is bad, you know, blue is good, and you can see this white circle, this black, what is black circle on here is the same white circle that I showed you on the previous slide of Jezero Crater. So you can see it's not an easy peasy place to land. All of these red zones are quite pervasive in this landing area, and we're trying to find the blue, you know, the blue little dot. So this white line is where Perseverance came in on the day of landing, and the dot here is where it actually landed. So you can see we were hoping that it would land, you know, somewhere in here. That's kind of where we put the center of the ellipse. But in the entry phase, we shot a little long, so we were in this kind of sea of rocks, and it did what it was supposed to. It found the little blue spot amongst the sea of red in this area. So after it picked that spot and flew to it, it landed within 5 meters of where it had chosen to go. So after the 300 million mile journey, we ended up landing pretty much 5 meters from where we had aimed to go, which I think is absolutely incredible. This is a little bit more detail on how it works. There's kind of a two-phase process where first we do a gross landmark matching, where we kind of look at 3 images in bulk and process them. And then once we have a good, understanding of where we are, and then we take more images and kind of refine that to better accuracy. And we had to work around a wide variety of operation, constraints of when we were going to land on Mars to make sure it worked under all those conditions. This is how the correlation actually happens. So this is the image as we take it from the descent camera. And then this is that same area cropped on the map and then normalized. So the algorithm picks features here and then cuts out little squares of those features and then normalizes them. And then compares, this normalizes here by taking them across the map and then finding where you get a peak where it actually matches the point on the map. So you get a peak for each of these templates, and then by having those, you basically have a spot, and then knowing the orientation of those templates, you rotate, and then you can say, oh, that must mean I'm here exactly. So what this looks like when it actually, and then we repeat it again with many, many more features on the find map to get a better estimate. What this looks like on the day of landing. So this is the actual data from the landing vision system on the day of landing. The big green squares are the features that we use to track. The descent image is here on the top right, and then the map is the one that's on the bottom right. So we're comparing these two. What's on the left here is the blue cutout of where we are on the map, just zoomed in. So you can kind of see here, we start with the big green squares, we get a lock, and then we go to the little ones. And as we descend, this blue square is getting smaller and smaller, because as we get lower, we're seeing less of the original map because we're much lower to the ground and the camera field of view is only so much. So you can see it get smaller and smaller, and then we do these divert maneuvers to actually go to the landing site. So you see it skew off to the right because the camera is only seeing a portion of the ground. It's looking in the air and it kind of comes back. We only expected it to work on the parachute. So the fact that it worked all the way to the ground was incredible, and is a huge deal, because that same technology gets fused in for the next mission, which is a sample retrieval lander. Green is good. These green squares, if it's green, that means it was good. We were able to use it for tracking. And the blue means basically it was good, but we had enough of what we needed, so we didn't need the blue. So the fact that we got a lot of green was also really good. It was a really good day to land on Mars. And with that, I can conclude. I just want to say that landing things on Mars, launch and landing, it's an incredible team effort. This is only part of the massive team that helped bring Perseverance to Mars safely. And just one head down in the corner. And this is probably one of the last pictures we took just before EDL of the team. This is the landing team holding up our lucky peanuts that we have to eat before every mission, just to make sure that the mission goes safely. That's our JPL tradition. And with that, I think I can close and open it up to any questions that people want to ask.
Thank you very much. Well, I am going to take the direct, or the speakers or the MC's prerogative and ask the first question. I just want to make sure that you were talking about the 7 minutes where it was falling and doing the mapping. That's autonomous, correct? That's, the people at NASA or at JPL are not doing anything with Percy. Percy is landing itself, essentially.
Yeah, so about everything about entry, descent, and landing is autonomous. About an hour before, maybe an hour and a half before entry interface, we actually turn off the transmitter for Perseverance. So that at that point, Perseverance cannot receive any more commands. So it's not just the 7 minutes, it's actually more than an hour or so before landing. Everything is on its own. We've actually coded it such that it can be like 2 to 3 days where it's just doing, everything is autonomous and we're just monitoring from the ground to make sure everything stays on track. When we turn the transmitter off, that's when like our hands are off in mission control. We can't tell it what to do. We're solely monitoring. Everything that we see is actually delayed because it takes 11 minutes or so. For the day of landing, it took about 11 minutes for light to travel from Mars to Earth. So we were getting all the information, but it was delayed by 11 minutes. So when it actually happened on Mars, Perseverance was on the ground, you know, when we heard it was a few minutes away from touching the top of the atmosphere. So over 500,000 lines of code, over like 30 pyrotechnic events that had to happen in that span of, you know, 17 minutes. And there were a lot of single point failures. So any one thing, if the parachute didn't work, it was game over. You know, if the radar didn't work, it was game over. And we had to build all of the autonomy for the vehicle to figure out what was going wrong and to do enough protection that it could get to the ground safely.
That just amazes me completely. So do we have any questions for folks in the audience for Dr. Mohan? Yeah. The question is, what information about Mars has Percy discovered so far?
That's a good question. I have to admit, I am not a geologist or a scientist. I know Perseverance has made a lot of discoveries over the last 2 years. I have mostly been following for the samples that it's been collecting. So it actually collected a set of samples and created a depot on Mars. And these samples range in different types. So like there was a sandy rock and a core rock sample. And that's the different science that I'm aware of. They were able to go to different regions of Jezero Crater and find different areas of habitability and have selected samples for them for eventual return to Earth in the next mission.
Yeah. How will the samples be returned to Earth? And
so
when?
there's a new mission. So it's a very complicated set of missions. The next one up to go get it is called Sample Retrieval Lander. It's slated to launch in 2028. And it is a lander which carries two things. It carries a rocket, the Mars Ascent Vehicle, and it carries two sample fetch helicopters. So Sample Retrieval Lander will land. Either Perseverance will still be alive and it'll come up and drop the samples there, or the helicopters will go grab the samples, pick them up, and put them in into the orbiting sample, which is this big canister that will go inside the Mars Ascent Vehicle. The Mars Ascent Vehicle will launch. The Sample Retrieval Lander will like push it, like throw it up, and then it'll ignite. Mars Ascent Vehicle will launch. First launch we've ever done off of another planet. It will deploy the orbital sample in orbit around Mars. A second mission called ERO. I forgot what the E stands for, but it's an ESA-based mission that will be in orbit around Mars. Will capture in orbit around Mars. Will capture the orbital sample, and then it will leave Martian orbit and come back to Earth. It will have put it into an Earth entry vehicle, which is kind of the third piece of it, and deploy the Earth entry vehicle back to Earth. And then that will land in the Utah test range somewhere in the 2035s. There's a really cool trailer. If I find it at the end of the day, I can send the link out. That shows how those samples will eventually get back to Earth.
Oh, so very easy. Very simple procedure.
If Perseverance was hard because there was one landing, one launch and landing is always kind of a critical. We've serialized like those critical events. So you have to launch Perseverance, land Perseverance, launch Sample Retrieval Helicopter or Sample Retrieval Lander, land Sample Retrieval Lander. So it's another 7 minutes of terror. And then you have to launch the Mars Ascent Vehicle. Then you have to capture it in orbit. And then you have to do another landing on Earth in order to get them back to the ground.
Yeah, sounds easy. Any other questions? Yes. Sure. So the question is, why weren't redundancies built into those single point failures?
We built redundancies in where we could, but there's only so much mass we can launch, right? And you saw for every pound that Perseverance increases, you have to increase all the other things as well, right? The heat shield has to grow, the back shell has to grow. You need more propellant in the cruise stage to manage it. So it's a balance between how much redundancy do you build in without it ballooning such that now you no longer can launch it, right? Because launch vehicle costs are almost by kilogram of the entire thing, not just the rover.
All right. Folks online can ask questions through the chat if you would like. But do we have any other questions? And is there one question? I can scroll. I don't see one. Anyone? All right. Well, if we could have one more round of applause for Dr. Mohan. Thank you. That I think you all are just wizards over there. So what we're going to do now is we're going to transition over to our telescope or observatory tour. Ian is going to handle that. So Ian, if you want to pop in and switch over. Dr. Mohan, you are welcome to stick around or take off as you would like.
I'm going to take off. Thank you very much for having me. I really
Thank
enjoyed
you
it.
very much for being here. Thank you.